So let's see if your prediction turned out to be right. After we got the same amount of metal as we have water, at least in weight, what we're going to do is we're going to speed up the heating of these two things, do that time lapse that we did before, and see if your prediction turned out to be right. So, did your prediction turn out to be right? It looks to me like the metal is having a much larger change in temperature than the water is, even though we have the same mass of each one of them. Which tells you that whatever the specific heat capacity is for copper, it's not going to be the same as water. It seems like it's changing temperature an awful lot faster. So let's see if we can explore why that might be. You're definitely going to want your notes out here because we're about to give you a definition for heat capacity. Okay, so I looked up this table of, well, they say specific heat. You notice I've been calling it heat capacity. The full name is specific heat capacity, and it's specific because of a reason that we're about to talk about. But let's look and see if everything makes sense up to this point. Water has a heat capacity of 4.18, well, we've been saying 4.184, right? You can see the heat capacities of these other things. And the thing that I'm noticing in here is we've got copper and we were comparing it to water. Now, why did we see such a massive increase in temperature? It went from 20 degrees to 80 degrees for the copper, and with more or less the same amount of heat, the water only went from about 20 degrees to 37. It had a much smaller change in temperature. Well, the reason is because of the heat capacity, because what this heat capacity says is it says you only need 0.385 joules of energy to raise the temperature of this copper by 1 degree Celsius. That's a pretty small amount of energy. Whereas with water, you need 4.184 joules of energy to raise water 1 degree Celsius in temperature. Now, obviously, we raise these things a lot more than 1 degree Celsius, right? So, but this is saying for each degree Celsius we changed, we needed to supply 4 joules of energy. That's a lot of energy to change the temperature of copper and of all the metals. Look at all the metals. Look how small they are. You need much less heat to change them by 1 degree Celsius. And that's why we're seeing such a massive increase in temperature for the metals. So this is the definition I want you to write down. Heat capacity, or more formally, specific heat capacity, is the amount of energy that you need to apply to raise the temperature 1 degree Celsius. Now there's one other thing I want to put in this. That's to raise the temperature by 1 degree Celsius if you're doing 1 gram of material. That's super important, and that's why they call it the specific heat capacity. It's specifically for 1 gram of material. So for copper, if you have 1 gram, and we don't, remember we had like 93 grams, but for 1 gram of copper you needed 0.385 joules of energy if you wanted it to go up 1 degree Celsius. So let's look at this example. I found there's this, I don't know if they're not really coins, but in any case, each one of these sort of coins is claimed by the author to weigh 1 gram. I stole these from the internet. But they claim that they all weigh 1 gram, which kind of surprises me, but maybe some are thicker than others, I don't know. But I noticed that they've got copper on here, and in our specific heat capacity table, we've got copper as well. It's 0.385 joules of energy needed to raise 1 gram of material 1 degree Celsius. Whereas, so we did copper, whereas silver, I noticed we have silver too, it takes 0.235 joules of energy to raise 1 gram of silver 1 degree Celsius. And they also have iron on here, right? So we did silver. They also have iron. Ooh, they even have lead. Iron is it takes 0.449 joules of energy to raise 1 gram of the material by 1 degree Celsius. And since they have lead, let's put it on there. Lead, it takes 0.128 joules of energy to raise it 1 gram of material by 1 degree Celsius. Now, if you looked at all of these and you said, which one of these would see the biggest change in temperature if you put all of them on my stove and you supplied all the same amount of heat, which one of these do you think would raise its temperature the most? Well, the answer would definitely be lead. The reason is it only takes 0.128 joules of energy to lift it 1 degree Celsius. So it won't take much heat to see the lead go up in temperature a lot. So this will have the biggest change in temperature. Now, if you were looking at the other three and you wanted to know which one of these would have the smallest change in temperature, assuming you apply the same amount of energy to each one, which one do you think would have the smallest change in temperature? Well, definitely the answer would be iron. Right, iron takes almost half a joule of energy, much more than the others, to lift it 1 degree Celsius in temperature. It's going to take a huge amount of energy to raise the temperature. So this would have a small change in temperature. So you can see if you look at metals though, compared to water, they all don't take very much energy at all to raise their temperature. That's why if you put metals on a stove, they get hot really, really quickly. You would not want to touch any of these, like even moments after you turn the stove on. But the water, you could dip your hand in the water for quite a while because it takes 4 joules of energy to lift 1 gram of that material by 1 degree Celsius. So it takes a lot more energy to lift the temperature of water. Okay, so if we understand that about a heat capacity, that things with really small heat capacities will increase in temperature rapidly, that means that anytime that we do this calculation, Q equals mc delta T, this value for C is no longer going to be 4.184 every single time. It's going to be different. We're going to have to look it up. And you remember that this metal that we're using right here, well, that metal is copper. And so we're going to have to use a different value than 4.184. So let's try this out. If we wanted to calculate how much heat it took to raise the temperature of this copper from 20.8 to 80 degrees, well, we would say Q equals mc delta T. The heat we would want to calculate is equal to the mass. Well, the mass was 93.30 grams. The specific heat is next. Well, we're not using 4.184, right? That's out. It's copper, so we're going to use 0.385. 0.385. And while we're here, I'm going to put the units in. It's joules per gram degrees Celsius. And then after that, we need delta T. And you remember, delta T is always the final temperature minus the initial temperature. Well, the final temperature, since we warmed it up, was 80.0 degrees Celsius minus our initial temperature was 20.8 degrees Celsius. And at this point, you remember, I always recommend doing the subtraction first and then multiply it times each one of these. And I get 2,126, I will say 0.5 joules, right? Joules is what's left because I cancel grams, I cancel my degrees Celsius, and I have joules left. So it takes about 2,000 joules of energy to raise this piece of copper from 20 degrees to 80 degrees. So exactly the same thing we did with water. It's just now we know that that specific heat is not always 4.184. Sometimes it'll be different. And for metals, it'll always be lower. Let's try a practice problem. And you know with practice problems, I'm going to ask you to pause the video and do your own calculation first. So it's definitely going to be a Q equals mc delta T question. And it has to do with iron. This is a picture of molten iron, what it looks like when you melt it. And you're going to need the specific heat table over here. You're probably going to want to find the specific heat of iron. And what I want to know is if iron melts when you heat it from room temperature up to its melting point of 1538 degrees Celsius. Wow, that's really high. If you wanted to melt an iron nail, which weighed 10 grams, so obviously a lot less than these people are doing here. We're talking like a little itty bitty nail like that. But in any case, if you wanted to raise it from that temperature to that temperature, I want to know how many joules of heat would be required. So go calculate that now.